class. All right, so we're talking about, let me write this down, 5.4, question 212. The question so we want to figure out, it's n, right? N goes from 1 up to infinity. So infinite sum of 1 over n squared minus n times sine what? Sine n, let me see, sine n. Okay, let me put a parenthesis around this n. So this n is an angle. So this is 1 over n squared minus n sine n. So the intuition is we probably want to compare with, oops, we probably want to compare with a p series, right? So automatically we're thinking, okay, can I make a connection in between those two? Right? Can we compare with this guy? Right? So this one we know, right? This one, 1 over n squared, is p series with p equals to 2. Because p equals to 2 greater than 1, we know this one converges, right? So known, this one, this is p series of p equals to 2, which converges, right? So this is the intuition. So probably we're thinking, okay, automatically I'm thinking about this one. Now, this one, and if we only pull out the n term, let me change the color. If we then only think about, let's call this an, let's call this bn, and we see when n equals to 1, this is always true. An is always, oh, this is bigger, right? Because the denominator, well, the denominator is up and down, right? Let's not make the, let me not make the conclusion about how to compare with those two yet. So automatically intuition is, okay, can I compare with 1 over n squared p series which converges? Now let's go back to see an. When we see an, because we know this is an alternating series. So because the sine n is bounded in between, so -1 less than or equal to sine n, doesn't matter what n is, right? And the positive 1. So sine n jumps between -1 and 1, so this is up. So an, let's call this an. Oh, no, let's not call it. So this series is not alternating. Right? Alternating series, if we remember from last class, we have if it converges, right? If it converges, it may converge absolutely or conditionally. Right? So those are something I could think of right away. Well, let's check more. So 1 over n squared minus n sine n. Right? So this is, no, what do I want to do? So this is in between. So let's only see this. So this is in between of 1 over, so it's less than or equal to n squared plus n, and we may not need this, but this is all something I could think of, n squared minus n, right? N squared minus n. And we see this is all positive. Even, you know what, this, I don't think this is an alternating series. Even sine is in between of -1 and 1, but it just keeps it to be positive. So it's not, let me rephrase this. So I don't think, actually, I don't think this is alternating series. I changed my mind. Because you see why? N squared minus n is always positive because n is natural number, 1, 2, 3, 4, right? Well, of course, n squared minus n is not so good. You know, we just delete this. It cannot be equal to, right? Because if n equals to 1, we will get 0 in the denominator. So for this one, just less than. We just take the less than. But other than 1, think about n equals to 2. 2 squared is 4. 4 minus 2 is 2. So it's always positive. So it's not alternating. So I changed my mind. And of course, n squared plus n is always positive, right? Always positive, even when n equals to 1. So now what do we do? So we don't get negative, positive. So it's not alternating series. Even sine n alternates from -1 to 1, right? But the series is not alternating series. The series is all positive, but it might be bigger, small, you know. It's not like, it's not monotone increasing or monotone decreasing series. So this one, it is confusing. Now I understand why you're complaining about this one. Anyone has any suggestions? Because this one, we definitely can compare with this, right? We can compare with this. And this one is always smaller than this. So we could put sign like this. It's always smaller than this. So the bigger one converges, the smaller one converges. That's for this one. But what about this side? Let me change my color. But we have the other part. So what about this? When we get 1 over n squared minus n, right? So this term is always greater than 1 over n squared. If the smaller one converges, we cannot see the bigger one converge. Okay? So this side, this one, all I can think of, that's 1 over n times n plus 1. Right? And we can break this into 2, or not n plus 1, n minus 1. N times n minus 1. So we can break this into 1 over n partial fractions minus, let's see, n minus 1 so we need the numerator to be 1 in the end. So let's see. So here we would have n minus 1 when we do common denominator. And here we would need n. So n minus 1 minus n, that's -1. So what do? We do this. So this one, we can do partial fractions. We get 1 over n minus 1, subtract 1 over n. Right? Then if we think about this, So I'm not going to write n equals 1 up to infinity anymore, okay? You can think about a series of this. So, and we know this part, so this is the alternating series. And we know by the book, this one converges, right? Remember the harmonic series diverges, but alternating, oh, hold on a second, this is negative. Oh, this diverges also, because we can pull negative sign up front, right? So we get a negative harmonic series. So we know this one diverges, right? We know this one diverges. And similarly, 1 over n minus 1, actually, let me write here. So we're considering this series, all right, minus 1 over n. Oh, okay. Okay. Right. So we need to consider this together. So, okay, I think I have a better idea now. So we don't have to do partial fractions. So with this one, we can do limit comparison. So this side, okay, so this side we're done, right? So for this part, we're done. We compare with this. Right? We see this part, because this one is in between of those two, is bounded in between those two series. So the upper bound is this one. Actually, we are done. Okay, I'm done. I don't have to prove anything. It's already proved. Okay, so AN, so this one, the upper bound, no, I think I have my signs wrong. No, this is lower bound. I'm so sorry. Hold on one second. Let me erase everything, start from very beginning. I think I have a better idea now. So we're doing this. N squared minus n times sine n. I don't really know the answer, off my head. I'm trying to figure out. So this one, because sine n is in between -1 and 1, so we can think, let's call this an. So an is bounded in between 2. So 1, we think sine n is negative, or sine n is positive. If sine n is positive, we'll have n squared minus n, right? Sine n is in between -1 and 1. -1 less than or equal to sine of n less than or equal to +1. So that's why this an is bounded in between 2. So this one is n squared minus n, right? The denominator is smaller, so the fraction is bigger. So this one is bigger than an, and then the other one is n squared plus n. The denominator is bigger, the fraction is smaller, right? So the lower bound we can compare with 1 over n squared, right? So this one, the lower bound, we can compare with 1 over n squared, right? Because the denominator is bigger and the whole thing, the fraction is smaller. So this is always smaller than 1 over n squared. Well, 1 over n squared, we know the series converges, so the smaller one converges. So this lower end is done. The lower end is done. If we could prove this one converges as well, then we're done. An is bounded in between of 2 convergent series, then we're done. So let's see this one. I have the idea to do comparison, to compare, so do limit comparison. So we're going to do limit So we're going to compare 1 over n squared minus n with 1 over n squared, right? If I compare with this, with n approaches to infinity, let's see if we get a number, or we get 0, or we get infinity. So 1 over n squared minus n divided by 1 over n squared, let's multiply by n squared, right? So I get n squared on top, right? Then limit of this, when n approaches infinity, what do we get? We get a 1, right? We get a 1. Just by ignore rule, or we can divide it by n squared. When we divide by n squared in the numerator, we get a 1. Divided by n squared in the denominator, we get a 1 minus 1 over n. Well, 1 over n, when n approaches infinity, becomes 0. So we have 1 over 0, 1, so which is a 1. So we get, so limit of the ratio, we get a 1. So in the limit comparison test, it says, okay, if the limit of the ratio equals to a number, not 0, non-zero number, so that means the two series, it's just one is a multiple of the other, right? The relationship is a scaling. So if one converges, the other one converges. If one diverges, the other one diverges. And we know 1 over n squared converges. It's a converging series, right? So we're done. So by limit comparison test, and this one converges as well. So we have a lower bound converge, we have the upper bound converge, and the an is in the middle, it must converge also. Does that make sense? Okay. So anyone, well, you're welcome. Well, anyone has any questions regards to this one? So this one is kind of, we have to think more about it. It's not very direct. You're welcome. Okay. All right. Any other questions? Yeah, so we converge, right? You see the an, we can consider, upper end and lower end. Lower end we compare with 1 over n squared right away because it's smaller than 1 over n squared. So 1 over n squared converges, so this one converges. And the upper one we go through limit comparison test to see this one converges also. Okay, any other questions we may have? Okay. I know we have covered a lot. Yeah, it's not only a lot of stuff is like, constructors of mathematics. It's not arithmetic anymore. It's not calculations anymore. It involves more and more. So when you go deeper in mathematics, it goes more and more about abstract thinking. So you see the constructors of sequence, constructors of a series. It doesn't look like a pure mathematics anymore, right? But they are mathematical. So if you go further to mathematics, it's all about abstract thinking. And yeah, so from time to time you may feel frustrated, but I'm here to help, and I really want to be helpful. Just let me know, if you do have questions, please let me know. All right, I have no problem to try with you to solve the problem. Because because this textbook is new to me. I don't have the answers, but one thing I could try is I could try with you. We can try together. So please do not get frustrated. All right, so we're here to learn. All right, we're here to learn. And you're young, you have a lot of times ahead of you. And also I know you're busy, your time is limited. So please do not get frustrated. Let's make it fun. Let's try to make it fun at least. Because sometimes if it's not fun, you know, we lose the savor of it, you know, we get frustrated very easily. Okay, any questions before I start talking about another test, something called a ratio test? So far we have covered in many tests, right? Okay, so now let's go back to talk about our new stuff. So we're going 5.6, I think. Ratio and root tests. Make sure. Okay. So this is a new test about the series. So one is called a ratio test. Well, ratio we know, right? We just did a limit comparison test. We take a limit of a ratio. So let's see this ratio test. So I'm going to read this. Consider a series AN. From our earlier discussion and examples, we know that the limit of AN goes to 0 if not, is not a sufficient condition for the series to converge. Not only do we need AN approaches 0, but we need AN approaches 0 quickly enough. What does it mean quickly enough? That means the rate of change is big, right? The rate of change is big. For example, consider series 1 over n, the harmonic series, and the series 1 over n squared, p series with p equals to 2. We know that 1 over n approaches 0 and 1 over n squared approaches 0. However, harmonic sequence series diverges, but 1 over n squared p series converges. Because the terms in the sequence 1 over n do not approach 0 fast enough as n approaches to infinity, right? Because 1 over n, right, the denominator is just n. But 1 over n squared, the denominator is n squared, right? N squared grows much faster than n. So 1 over n squared approaches 0 much faster than 1 over n. So here we introduce the ratio test, which provides a way of measuring how fast the terms of a series approaches 0. So that's the ratio test. So we have a series of AN. Let this be a series with non-zero terms. So let rho, so this is read as rho, R-O-U. Rho equals to limit n approaches to infinity, absolute value of AN plus 1 over AN. Okay, in the limit comparison test, we take a limit of ratio, but that ratio is AN with BN. So we're comparing two series, right? So this ratio test, this ratio is two consecutive terms in the same series. So the AN plus 1 term over AN term. So the n plus 1's term in the numerator and the nth term in the denominator. So why do we comparing those two terms? You know, we want to compare, so the ratio will show us the change of those two, right? So from AN to AN plus 1 measures the change. So first, if rho is in between 0 and 1 and is less than 1, it could be 0. So if the limit is 0 or less than 1, but non-negative, right? Because it's an absolute value, right? So at least it can be 0. So basically, we're considering this limit less than 1. If this is less than 1, what happens? We know the numerator is always smaller than the denominator, right? So which means the next term in the series is always less than, so it's a decreasing series. So if rho is less than 1, then the series converges absolutely. Converges absolutely. So the second one is saying if rho greater than 1, well, think about it. If this absolute value is greater than 1, for now we're just considering, all positive, right? By doing absolute value, we force it to consider its absolute value all positive. So if rho is greater than 1, that means the numerator is bigger than the denominator. So the next term could be, a bigger than previous one. Or rho goes to infinity. There's no limit of this ratio. So which means what? Which means the numerator is far bigger or grows far faster than the denominator. Then this series diverges, right? If we think about it, this is kind of intuitive, right? Diverges. So the third one is if rho equals to 1, if the limit of the ratio equals to 1, right? The test does not provide any information, so it's inconclusive. So we cannot draw any conclusion. So basically we focus on the first one, right? If the ratio is greater than 1, okay, diverges. And or the limit does not exist. Well, if the limit equals infinity, that means the limit does not exist, right? So greater than 1, so we can, consider the two situations in one. So as long as it's greater than 1, of course includes, it be infinity, then the series diverges. So if it's less than 1, it converges absolutely, right? Converges absolutely. So that's the 3 parts. If it equals to 1, it's inconclusive. All right. So the difference between ratio test and the limit comparison test is here we're taking ratio of the neighbors of next two terms, the two terms next to each other. So basically, we want to measure the speed of the next one, how fast this is changing. So if the ratio is less than 1, we say it converges absolutely. If it's greater than 1, we say it diverges. If it equals 1, we cannot make any conclusion. Okay, now let's see an example. Okay, are we ready for example? Okay. All right, so let's go for an example. So we're going to prove. I'm going to skip the proof because this is for pure mathematics majored. Because when I was learning this, because my major was mathematics, so I have to learn how to prove all this. But for this class, we don't need to prove all this. Okay, let's see this example. The first example is 2 raised by n divided by n factorial. Oh, both grows very fast, right? So with the knowledge we know before calculus, so we probably, it's difficult to tell, which one grows faster, the numerator grows faster or the denominator grows faster. So how fast this one goes to 0 or maybe never goes to 0 if the numerator is much bigger than, grows much faster than the denominator. Factorial grows very, very fast, right? If you want to get some, intuition, you could write down some terms. N equals 1, get 2, n equals 2, we get 2 squared over 2, we get 2, n equals 3. Let me type in the chat actually. So we get some intuition, right? Let's see. N equals 1. We will get 2 over 1 factorial. Well, 1 factorial is just 1. right? So we get 2. The first term. Well, n equals 2. We get 2 squared divided by 2 factorial. Well, again, 2 factorial is 2 times 1, this is 2. But 2 squared is 4, so 4 divided by 2, we also get 2. So the second term is also 2. Well, n equals 3, we get 2 raised by 3 divided by 3 factorial. And the 2 raised by 3 is 8. 3 factorial is 3 times 2 times 1, which is 6. Right, so we get a 4 over 3. Oh, we see it seems like it's decreasing, right? So let's do more. N equals 4. So n equals 4, we get 2 raised by 4 divided by 4 factorial. So 2 raised by 4 is 16, right? 2 times 3 is 4, 4 times 4 is 16, over what's 4 factorial? 4 factorial is 4 times 3, 12, 12 times 2, 24. 24 times 1 is still 24. 24, then we can simplify 16 over 24. So this is 2 over 3, right? Because the common factor is 8. 2 times 8, 16, 3 times 8, 24. So 2 over 3. Oh, we see this, right, decreasing. Let's do one more. N equals 5. So 2 raised by 5 divided by 5 factorial. Well, what's 5 factorial? Well, what's 2 raised by 5? 32. 5 factorial is 5 times 4 times 3. But we just do 5 times 24, right? 2 raised by, let me see your comments. Oh, 120 already, you already give me 120. 5 times 24, right? Because 5 factorial is 5 times 4 factorial. We already know 4 factorial is 24, so 5 times 24, 120. Thank you, Damon. And then we simplify. We simplify by 4, right? Let's simplify. We can simplify by 8. So we get 4 times 8 is 32. So what's 120 divided by 8? 15, isn't it? Yes. So 4 over 15. So what's our conclusion? We could do more, but we could make a conclusion here. The denominator grows much faster than the numerator, right? So this is just an intuition. Now let's do ratio test. So ratio test, we want to compare 2 raised by n plus 1 over n plus 1 factorial with divided by 2 raised by n divided by n factorial, right? So we basically take a limit of the n plus 1 term, an plus 1 term over an term. So let's do that. So rho equals the limit, as n approaches infinity, 2 raised by n plus 1 divided by n plus 1 factorial, then over the nth term, which is 2 raised by n divided by n factorial. Well, 2 raised by n plus 1 over n plus 1 factorial divided by 2 raised by n over n factorial, that's just multiplied by n factorial divided by 2 raised by n. So 2 raised by n plus 1 can simplify with 2 raised by n, we just get 2, right? And n factorial over n plus 1 factorial, just get 1 over n plus 1. So we get 2 over n plus 1, right? So that's just limit of 2 over n plus 1. Well, as n approaches infinity, of course, 2 over n plus 1 goes to 0. So by the first condition, so the limit of the ratio equals to 0. By the first condition, right, it says rho less than 1. Less than 1. And we don't, because for us, we didn't do absolute value, right? Because we have all positive terms. We didn't really put an absolute value sign, which means absolute value sign means we can deal with alternating series, right? Sometimes we get an alternating series, we can put absolute value sign. So by the first one, this series converges. The intuition is the denominator grows much, much faster. So that means this series, the terms goes to 0 very, very fast. So the calculation is this. So we take the limit as n approaching infinity, where the numerator, so it's a ratio. The numerator is n plus 1 term. The denominator is nth term. Then we just do the calculation. The rest is just algebra, right? So we get 2 over n plus 1. Then we take a limit as n approaching infinity. So this does equal to 0. And so this series converges, and it converges absolutely. Well, this is not an alternating series. We just see converges. If it's an alternating series, we see converges absolutely. Okay, anyone has any questions? All right, let's go to the second one. So second one, the numerator is n raised by n, right? The denominator is n factorial. Oh, let's do a couple of, let's try to do a couple of, first term, second term, to get a feel about it. We can go ahead and approach, apply ratio test. Or, we can get to know this series a little bit. So 1 over 1 raised by 1 is 1. N factorial is just 1, so the first term just 1. Right? The second term n equals to 2. We get 2 raised by 2, which is 4, over 2 factorial, which is 2. So we get 2. The first one is 1, the second one is 2. So n equals to 3. So we have 3 raised by 3, or 3 raised by 3 is 27. Right? 3 raised by 2 is 9. Then so we have 27 divided by 3 factorial. 3 factorial is 3 times 2, 6. Right? We can simplify a little bit, so we get a 9 over 2. So it gets bigger. So n equals to 4. So we get 4 raised by 4. Wow, what's 4 raised by 4? Divided by 4 factorial. 4 raised by 4. 4 times 4, 16. 16 times 16. 16 times 16, what is it? 254? Right, because the 4 raised by 4 is 2 raised by 8. 256, okay. So 256 divided by 4 factorial is 24. So we can simplify. Let's simplify by 2. Oh, you know what? Let's do this. I don't have to do the calculation. It's 4 raised by 4. It's 4 raised by 3 divided by 3 factorial. 3 factorial is 6, right? And 4 raised by 3. So we can do 4 times 4 squared, 4 times 16 divided by 6. And then we can simplify with 2. So we get 2 times 16 which is 32, and the denominator is just 3. So we get a 32 over 3. So this is about a 10 point something, right? And before, so 9 over 2, that's 4.5. So we see this sequence, the numerator grows much faster than the denominator. Maybe, maybe we can do more. So this means, so the intuition is, the numerator, so this term is an increasing term. So let's just go ahead. So that's our intuition, right? Now let's go ahead, apply ratio test. So we're going to do n plus 1 raised by n plus 1 divided by n plus 1 factorial, then divided by n raised by n divided by n factorial. Basically, the n plus 1th term divided by nth term. So we take a limit as n approaches infinity, 2 raised by n plus 1 divided by n plus 1 factorial. So this is the n plus 1 term. Then the denominator is 2 raised by n divided by n factorial. So this is the nth term. That's a, not b factorial. Oh, I'm so sorry. Why am I going back to? I'm going back to talk about a. Right. Thank you so much, Damon. So b, so the n plus 1 term is n plus 1 raised by n plus 1 divided by n plus 1 factorial. The nth term is n raised by n divided by n factorial. Now we just do the calculation. So n plus 1 raised by n plus 1 divided by n plus 1 factorial multiplied by n factorial divided by n raised by n. N factorial. Okay, all right. So n factorial divided by n plus 1 factorial, that is 1 over n plus 1. Right, so we get 1 n plus 1. Then n plus 1 raised by, then we have n plus 1 in the denominator. N plus 1 raised by n plus 1, we can break it into n plus 1 raised by n times n plus 1. So we get n plus 1 in the numerator. Numerator we have n plus 1. Denominator we have n plus 1. That becomes 1. Right. So we're left with n plus 1 raised by n in the numerator and n raised by n in the denominator. So we can combine, we can write that as, because both raised by n, we can write as n plus 1 over n, then both raised by n. And remember, limit and power can be switched, right? So limit of a thing with a power, limit of an expression with a power, we can take a limit of the expression, then raised by power. Right? Or if we remember the definition of Euler number, if we remember definition of Euler number, this is exactly Euler number. All right, limit as n approaches infinity, n plus 1 over n can be written as 1 plus 1 over n raised by n. That equals e, right? E raised by 1, because this is 1 over n. If we remember, if we would get it 1 plus 2 over n, that's going to be e squared. If we have 1 plus 3 over n, that's e raised by cube, so on and so forth. So this one just definition of e raised by 1. Right. So rho is a number of e. What's the Euler number? 2.712, goes on forever, just like a pi, irrational number, but it's bigger than 1. So if it's bigger than 1, we'll go back to the ratio test. The second one says, if the limit of the ratio bigger than 1, the series diverges. If the limit of the ratio greater than 1, the series diverges. So this B diverges. So the intuition is the numerator grows much, much faster than the denominator. So it will never approach to 0. So the second one, right? So the limit of the ratio equals to Euler number, which is greater than 1. By ratio test, this series diverges. Anyone has any questions? I'm not sure how you reduce from line 2 to line 3. From line 2 to line 3. Oh, okay. Let's do the calculation. So we have n plus 1 raised by that. Let's go to the whiteboard. So that's algebra. So we have n, oops. We have n plus 1 raised by n plus 1 divided by n plus 1 factorial. So this is the n plus 1 term. Divided by n raised by n over n factorial. We're going to write as multiplied by n factorial divided by n raised by n. right? Well, what's n factorial? How do we simplify n factorial? And so those two can simplify, right? Those two, when we simplify n factorial, n plus 1 factorial, n plus 1 factorial, that equals to n plus 1 times n factorial. Think about 5 factorial, right? If it's a 5 factorial, it just equals to 5 multiplied by 4 factorial, right? Because that's the definition of factorial, right? We just multiply the number next down onto 1. So n plus 1 factorial equals to n plus 1 n factorial. So this one I can write as n plus 1 times n factorial. Then n factorial divided by n factorial becomes 1. So at the denominator, I'm left with n plus 1 times n raised by n. Now, n plus 1 raised by n plus 1, I can also rewrite, right? Because I can write as n plus 1 raised by n multiplied by n plus 1. Right? So n plus 1 raised by n plus 1, I break up into n plus 1 raised by n multiplied by n plus 1 raised by 1. Or raised by 1, I don't bother to write it. So now you see we have n plus 1 over n plus 1. So numerator will have n plus 1, denominator will have n plus 1. So this becomes 1. So we're left with n plus 1 raised by n and n raised by n. So n plus 1 raised by n in the numerator, n raised by n in the denominator. Because both raised by n, so we can write it this way. Right? Because they have the same power. Does that make sense? Okay. So Paul asked this question. Who asked this question? Okay. All right. Let's go back. Okay, so that's 2. That's B. So B diverges. But now let's see C. C, we have alternating series. So we have -1 raised by n, n factorial square, and 2n factorial. So we're going to do the ratio test again. So -1, so n plus 1 term, so everything is n plus 1 instead of n. So -1 raised by n plus 1, n plus 1 factorial, then square. So that means n plus 1 factorial times n plus 1 factorial. Then divided by 2 of n plus 1 factorial. Then divided by the nth term. Nth term is -1 raised by n factorial square, and then divided by 2n factorial. So the rest is just calculation. So -1, so because it's absolute value, right, we can forget about -1 raised by n plus 1, right, because no more negative terms. So we have n plus 1 factorial square. Well, what's that? That's just n plus 1 factorial times n plus 1 factorial. Then divided by 2 multiplied by n plus 1, we can distribute 2, so we get 2n plus 2 factorial. Divided by a fraction, we continue to be multiplying. Multiplying is inverse. So we get 2n factorial in the numerator, and then we get an n factorial square in the denominator. N factorial square, again, is n factorial times n factorial. So n plus 1 factorial, again, is n plus 1 times n factorial. So we have n plus 1 square left in the numerator, because n factorial divided by n factorial becomes 1. And the 2n factorial with 2n plus 2 factorial. So 2n plus 2 factorial, let me write in the chat. 2n plus 2 factorial equals to 2n plus 2 times 2n plus 1 factorial, which is 2n plus 1, then 2n plus 0, which is 2n factorial. Right? So 2n plus 2 parentheses factorial equals to 2n plus 2 times 2n plus 1, because the next one is 2n plus 1. Then the next one is 2n factorial, right? So we have 2n factorial and 2n factorial canceled. So we're left in the denominator of 2n plus 2 and 2n plus 1 term. Then we'll take a limit of this, right? We'll take a limit when n approaches infinity of this. By ignore a rule, we just take the leading terms. Leading terms in the numerator is n squared. Leading terms in the denominator is 4n squared. So n squared divided by 4n squared, it is 1 over 4. So limit of that is 1 over 4. And 1 over 4 is less than 1. So by the first part of ratio test, this series converges. Any questions? So it seems like ratio test could have a lot of calculations, algebraic calculations. Anyone has any questions? Okay, if not, I guess we're ready for the practice. Okay, everyone try 5.21. All right, so I have n cubed divided by 3 raised by n. You could go ahead and apply ratio test, or if you want to give yourself some intuition, you can write down the first couple of terms to see if it's n cubed grows faster or 3 raised by n grows faster. You can also think about the graph. N cubed, the graph of n cubed, right? And also you can think about 3 raised by n. 3 raised by n is exponential function, right? And the n cubed is a polynomial function of degree 3. Okay, I'll give you a couple minutes to try this. So what you need to do is you need to write down the n plus 1 term, then take a ratio of n plus 1 term with this n term, then try to calculate the ratio, then take a limit when n approaches infinity to see what you get. If you get a number less than 1, you can conclude by ratio test it converges. If you get a ratio greater than 1, or you don't get a ratio, you get infinity, by ratio test it converges. If you do get 1, it's inconclusive. All right, so Paul already done. He got 1 over 3, saying it's convergent. Paul, we don't really need to use absolute because we're not dealing with alternating series, so convergent is enough. But it's okay if you say absolute convergent. So 1 over 3. Or Ali also get 1 over 3. Because we have n plus 3, so let me do in the chat. I have n plus 1 raised by 3 divided by 3 raised by, so so 3 raised by n plus 1, right? 3 raised by n plus 1. Then I'm going to multiply by the inverse, so which is 3 raised by n over n raised by 3. Right. Okay, James also, Golem also got 1 over 3. So I can simplify. So 3 raised by n plus 1, simplify with 3 raised by n. So I get 3 in the denominator. And then I get n plus 1 raised by, you know what, I cannot even see my own calculation. So I get n plus 1 over n. Let me use another bracket. Raised by 3, right? Then what I get a 1 over 3. So I get a 1/3 of this. Basically, I get 1 over 3 of this. Right. So after the algebraic calculation, so 3 raised by n over 3 raised by n plus 1, I get a 1/3. Then n plus 1 raised by 3 over n raised by 3, I can write it as n plus 1 over n raised by 3. Then when I take a limit of this, right? So limit of n plus 1 over n, that's 1. So 1 times 1/3, that's 1/3. Yes, I agree with you guys. So what's the conclusion? Yeah, so limit equals 1 over 3 is less than 1 by ratio test. So when you answer questions like this, you have to see by ratio test. So it's less than 1 by ratio test. This series converges. All right, great. Let's keep going. Anyone has any questions? Okay, so the next one is a root test. It's a root test. So the approach of the root test is similar to that of the ratio test. Consider a series of an such that the limit of the nth root of that equals rho. So rho, before we take a ratio of the next two terms. But now we're going to take nth root of absolute value of the term. All right. So then for n sufficiently large, a absolute value of an approximately equals rho raised by n. Therefore, we can approximate absolute value of an by writing like this. So the expression on the right-hand side is a geometric series, right? Because rho raised by n plus rho raised by n plus 1, so on and so forth. That's geometric series. As in the ratio test, the series of an converges absolutely if rho is less than 1. And the series diverges if rho is greater than 1 or equals 1 is inconclusive. So if rho equals 1, the test does not provide any information. So for example, for any p series, 1 over n raised by p, we see that rho equals limit. We take a nth root of this, absolute value of n raised by p. That equals the limit of 1 over n raised by p over n. So to evaluate this limit, we use the natural log function. Doing so, we see that we take a log on both sides. We take a log on both sides because we want to send the exponent to be in up front, right? We take a log of this because the limit and the log can switch, can be swapped. So limit of a log is log of the limit. And so in the end, what do we get? We get a limit of rho p ln of 1 over n over n. So we use L'Hopital's rule. It follows that ln rho equals 0. And therefore, rho equals 1 for all p. So however, we know that p series only converges if p greater than 1 and diverges if p less than 1. So we don't. So this is the reason for ratio for root test. Okay, you're not a mathematics major, so let's not care about that. Let's go ahead to theorem. So root test. So consider the series of an. So we let rho be the limit of n approaching infinity. We take nth root of absolute value of an. So which means we can deal, so an can be positive, can be negative, can be, so this can be alternating series. Okay, so just like the previous one, like a ratio test. ratio test we can also use for alternating series. So that means this one, by putting absolute value sign, means this applies to alternating series. So we take the nth root of that. Now we have three situations. If the limit is less than 1, then the series converges absolutely. Okay, similar to ratio test. If rho greater than 1 or rho equals infinity, then the series diverges. Right, same as the ratio test. Third, if rho equals 1, the test does not provide any information, so inconclusive. So I think that's why they put those two tests together, because the three conditions are exactly the same, right? So the first one is ratio test. The ratio test will take the ratio of n plus 1 term with n term. The conclusion is the same, 1, 2, 3. So the root test is we just take the nth root. We just take the nth root of the term. Okay, let's see an example. So the first example is n squared plus 3n raised by n over 4n squared plus 5 raised by n. Well, this can be written as n squared plus 3n over 4n squared plus 5, then raised by n, right? So with this, we want to take nth root. When we take nth root, we just have n squared plus 3n over 4n squared plus 5. So we take the nth root, we take the limit, we take the nth root of the term, n term, then n over n that becomes 1, right? The power and the index are the same. So n over n equals 1. So that's the same as the limit of n approaching infinity, n squared plus 3n over 4n squared plus 5. Well, by ignore root, right? By ignore root, we just ignore the lower terms. We just take the leading term in the numerator, we take the leading term in the denominator. So we got n squared divided by 4n squared. That's just 1 over 4. Well, 1 over 4 is less than 1 by ratio test, by root test. By root test, the first part, right? Because the limit is less than 1, so the series converges, right? Converges. And this one is all positive, right? This term is all positive. We don't really have to say converges absolutely, because when we see converges absolutely, that's to see for alternating series. But you know, it's fine if we really see it. So root test just removes the power of n. Exactly. Just remove the power. You're exactly right. Well, so anyone has any questions about this? Exactly. Yeah. Because if this is n, we just take n's power. Yeah. Okay, let's see the second one. The second one is n raised by n over ln of n raised by n. Of course, we're going to take n's root. So when we take n's root, we just have a limit of n over ln n. Right? The numerator is a linear function. The denominator is log function. And the log function grows much faster. Right? Because when n goes to infinity, the numerator goes to infinity. The denominator goes to infinity. Right? So the indeterminate form. So we can use L'Hopital's rule. We take a derivative of n that equals 1. We take a derivative of ln n that equals 1 over n. So 1 over n that equals n. So when n approaches infinity, this approaches infinity, which means the log function grows much faster than linear function. So because this goes to infinity, the limit of this nth root of the an term goes to infinity. So by root test, by the second part of a root test, the series diverges. Okay. The series diverges. Okay, anyone has any question about this? All right, so now let's go to 5.22. So use root test to determine whether the series 1 over n raised by n converges or diverges. Okay, everyone try this, please. And some of you, please try to participate. Equals to 0 converges. Yes, yes. When we take an nth root, we just get a limit of 1 over n. When n approaches infinity, 1 over n approaches 0. So 0 is less than 1. So by root test, this series converges. All right. So examples like this is simple, right? But when you take a final exam, if I ask you questions, you have to tell me by which test, right? You have to say, okay, you take an nth root, show me you take an nth root of this, you take a limit of nth root, then equals 0, you say, okay, by root test, this series converges. Okay, good. Easy, right? All right. So, yeah. Okay, anyone has any questions? Okay, yeah, sometimes math is easy, sometimes it's a little bit annoying. But when math gets annoying, if you like math, that's the fun part. But if you don't like math, forget about it. This test feels like a shortcut more than the others. Yes, it's an easy test. Okay, now it talks about choosing a convergence test. It says at this point, we have a long list of convergence tests. However, not all tests can be used for all series. When given a series, we must determine which test is the best one to use. Some series we may use different tests to prove. So here is a strategy for finding the best test to apply. So this is a problem-solving strategy. So consider a series of AN. In the steps below, we outline a strategy for determining whether the series converges. So is AN a familiar series? For example, is it the harmonic series which diverges, or the alternating harmonic series which converges? Is it a P series, or geometric series? If so, check the power of P. If P is greater than 1, we know P series greater than 1 converges. P series, when P less than 1, it diverges. If it's geometric series, we know the ratio. So the absolute value of the ratio, if it's less than 1, it converges. And if it's greater than 1, it diverges. So second one, is it an alternating series? Are we interested in absolute convergence or just convergence? If we are just interested in whether the series converges, apply the alternating series test. If we are interested in absolute convergence, proceed to step 3. Consider, so we're going to do 3. Considering the series of absolute values. Okay. So 3, is the series similar to a P series or geometric series? If so, try comparison test or limit comparison test. all right? So this also works for the second part. Second part, if we consider absolute convergence, we also use step 3. 4, do the terms in the series contain a factorial or power? If the terms are powers such that an equals bn raised by n, try the root test first. Otherwise, try the ratio test first. 5, use the divergence test. Right? If we have a feel about a divergence, can read a couple of terms. Right? If the numerator grows much faster than the denominator, and use the divergence test. If this test does not provide any information, try the integral test. Right? So we have to try to remember all those tests. So that's the annoying part for this chapter. Right? We have to try to remember different kinds of tests. And then we have to remember, in what situation, which one is better to apply. Because for now, for your homework, because the homework is under each section, and you know exactly which one to apply. But in final exam, you don't have the convenience, so you have to figure out which one to apply. So this is like a strategy list. Anyone has any questions? It's good to try. It's good to write down and all the tests on the side, right? Then just one day write down all the tests or get all the tests on your side. Other day just randomly pick up some from homework, right? Then to try it. Will all the convergence tests be on the final? If not, what percent of them will be like half? Yeah, I would say at least one of each. Okay, one of each. Or sometimes, yeah, like that, one of each at least. All right. Okay, any other questions? Excuse me. Oh, that's an interesting question. They may say, what if we select the improper test, but still get the right answer? Well, partial credits will always apply. Even sometimes you're not 100% right, but I'm still looking for the right places to give you credits. Does that make sense? And this strategy, right? This strategy tells you, whenever you try, you think about those famous series first, like a harmonic series, right? Like 1 over n, diverges. If I give you a series, it's always smaller. The term is always smaller than, always bigger than harmonic series, right? Let's think about 1 over n minus 1, right? Just think 1 over n minus 1 or 1 over 2n minus 1, things like that. And then it diverges also. Why? Because it's smaller than harmonic series. I mean, it's bigger than harmonic series. And the smaller one converges. So harmonic being smaller one compared to it diverges. So the bigger one must diverge. Right? So 1 over n harmonic series diverges. Then P series, right? We have used 1 over n squared many times, right? If we're giving you, let's say, a smaller series, right? Let's say 1 over n squared plus 1 or something. And you know that, by intuition, you know that one converges as well because it's smaller than that. But then how would you show it? How would you show it? You could just tell me by analysis, or you could show it by comparison test, right? Comparison test, limit comparison test is very useful. Because when you take a limit, you compare the ratio of two series. If you get a number, non-zero number, right? It says, oh, one series does, one series converge, the other one does. One series diverge, the other one does, the other one diverge. So, right? And also think about, if it's a P series or geometric series, right? If P series, let's see, 1 over square root of n, or 1 over cubic root of n. You know that's a P series, right? The P equals half, P equals 1/3, right? Because it's less than 1, so it diverges, right? If I give you like a 1 over n raised by 3, n raised by 4, n raised by 5, you know that's a P series with P greater than 1, so it converges. Okay, so those are the easy ones. And also geometric series, right? If you see a geometric series, then you just check the ratio, check the rate, right? Check the rate, and if it's less than 1, if the absolute value is less than 1, you know it converges. If it's greater than 1, it diverges. And if it's less than 1, you even know, the series converges to a certain number. Remember, the first term divided by 1 minus the ratio, right? So that's the first part. So first part covers a lot already. A second part, if you see -1 raised by n or -1 raised by n plus 1, right? If you see that, you think about, okay, let me try alternating series test, right? Try alternating series test. And then you can figure out, if it converges. If it doesn't converge, it diverges. If it converges, you can figure out, if it's a absolute convergence or conditional convergence. Right? Also, if it's similar to P series or geometric series, right? Because some alternating series is alternating P series or alternating geometric series or alternating harmonic series. If so, try comparison test or limit comparison test. Well, if the terms we see factorial or power, we want to use, especially if we see it's raised by n power n, we can use a root test. Right? And ratio test is it's an easy one, and is also often used one, especially when factorial and power involved, because we can cancel many terms. You see n plus 1 factorial, right, equals to n plus 1 times n factorial. So when we divide by n factorial, we just left with n plus 1. Then in the end, we see, okay, if nothing works, we go to divergence test, right? If nothing works, we go to integral test. Anyone has any questions? Okay, let's see this one. We have this bunch. We have A, B, C, D. A, we have n squared plus 2n over n cubed plus 3n squared plus 1. The second one, we have alternating series. The numerator is 3n plus 1, right? It's a linear function. The denominator is n factorial. C is e raised by n, denominator over n cubed. And D is 3 raised by n over n plus 1 raised by n. You see D is inviting you, right, to use root test, right? And the C is inviting you to use a ratio test, right? Also, we see B, we see factorial, you know, we can use ratio test. And the first one, A actually, we can use different tests for this. Okay, let's see this. So A, the series is not a P-series, not a geometric series, not a harmonic series, right? So the series is not alternating. And for large values of n, the limit of the nth term just equals 1 over n, which goes to 0, right? So it seems like, you know, we like to apply comparison test or limit comparison test by comparing with whom? Because it's 1 over n, right? When we take a limit of it, we get 1 over n. So we want to compare with 1 over n. So if we use a limit comparison test, and we see limit of this with 1 over n, what do we get? We get a 1. So limit comparison test is saying if the limit of the ratio equals 1, one converges, the other one converges. One diverges, the other one diverges. So 1 over n diverges. So that means this series diverges as well. Right? Does that make sense? This is a rational function, right? Of course, we can use integral test, but we don't want to go that far. Because if we can use the easy one, we use the easier one. Okay. So B we have alternating series 3n plus 1 over n factorial. So this one better converge because the numerator is just linear function and denominator is factorial, and factorial grows so much faster than linear function. So that means the term goes to 0 so fast. So the book says, okay, step 1, the series is not a familiar series. Step 2, the series is alternating. Since we are interested in absolute convergence because we're considering this convergent, right? Consider the series of absolute value of it. Absolute value of it is 3n over n plus 1 factorial without a -1 raised by certain power. Step 3, the series is not similar to a P-series or geometric series yet, right? No. Since each term contains a factorial, apply the ratio test, right? So when we see factorial, or sometimes exponential function, so we may think to apply ratio test because we can simplify a lot of terms. So we can apply ratio test. So we get 3 of n plus 1. 3 of n plus 1 divided by n plus 1. Oh, this is a typo. So this should be 3n over n factorial, not 3n over n plus 1 factorial. Right, let's go back to check. It is n factorial. Yeah. So it's a 3n plus 1 over n factorial. So this is just a typo. So this should be written as 3n plus 1 in the numerator and n factorial in the denominator. Just typo. So when we do that, the nth term is 3 of n plus 1 plus 1. All right. Then over n plus 1 factorial. Then divided by 3n plus 1 over n factorial. So this also has a type O in it. So this one should be 3 of n plus 1, then plus 1. But of course, you know, those constant terms, when n goes to infinity, doesn't really do anything. So the answer is still the same. So the numerator will get 3n plus, should be 4, should be 3n plus 4, because we have to add 1 to it. Over n plus 1 factorial, multiplied by n factorial, divided by 3n plus 1. Then n factorial divided by n plus 1 factorial simplified to be just n plus 1. So the numerator will have 3n plus 4 over n plus 1 times 3n plus 1. Well, limit of this when n goes to infinity, just apply, ignore rule, right? Just take the leading term of the numerator, which is 3n. Take the leading term of the denominator, which is n times 3n, which is 3n squared. 3n over 3n squared is just 1 over n. 1 over n. So limit of 1 over n when n goes to infinity, that goes to 0. Right? So by ratio test, because the limit of the ratio equals 0, so that conclude this series converges. Right? This series converges. And we conclude the original, the alternating series converges absolutely, because we take the absolute value of it. Right? We just ignore the negative signs. Because we ignore the negative signs, this series is a much bigger series. Right? This much bigger series converges. The smaller one, the alternating one, is much smaller one, must converge. So it converges absolutely. Anyone has any questions? Sorry, that's just type O here. All right. So this should be 3n plus 1 in the numerator, n factorial in the denominator. And here it should be 3 of n plus 1, then plus 1. So this should be 3n plus 4. So that's typo here. So C, we have e raised by n, exponential function. And the denominator is n cubed, with a polynomial of degree 3. So the numerator grows much, much faster than the denominator. So the intuition is this series diverges. So what do we want to do? We want to use a comparison. We want to use a ratio test. All right. So this is inviting us to use ratio test. So we will do e raised by n plus 1 divided by n plus 1 raised by 3, then divided by this nth term. So C, step 1, the series is not a familiar series, which means not a p-series, not a geometric series, it's not a harmonic series. So step 2 is not an alternating series, it's not. Step 3, there's no obvious series with which to compare this series with. It's not like a 1 over n squared, right? It's not like a rational function we can compare with some p-series or harmonic series. Step 4, there's no factorial, but there is a power. It's not the ideal situation for the root test. And step 5, to apply the divergence test, we calculate that, we could apply divergence test, right? If the limit of the term goes to infinity, that means the series diverges, right? So what does this mean? This means, you know, the numerator grows so much faster than the denominator. So when n approaches infinity, the denominator basically diminished, you know, just doesn't contribute much. So the limit of the nth term goes to infinity. So that's done. We don't really have to go to ratio test, but we could use a ratio test. If we use a ratio test, we'll get the same result. It will prove this divergence also. But we could use a divergence test because we know the numerator grows so much faster than the denominator. So which means, you know, when n goes to infinity, the denominator just, you know, doesn't contribute anything. So the limit of the nth term goes to infinity. So by convergence test, this series diverges. So that's this one. Anyone has any questions? The intuition part of ratio and root test is unnecessary, right? Well, it's still necessary. It's still necessary, right? For you know, so this sometimes a lot of times we do mathematical analysis. You know, we don't really prove by certain principle, but by analysis, right? So what does it mean? What's the mathematical analysis of limit of n approaching infinity u raised by n over n cubed equals to infinity? The mathematical analysis is the numerator is exponential function. And we know exponential, the graph of exponential function, right? It just shoots to infinity so fast. And we know the graph of n cubed, polynomial of degree 3. This grows much slower. It grows faster than linear function, right? But it grows much slower than exponential function. So in life, you know, everyone pursue exponential profits. So we know exponential function grows really fast. All right, so last one is inviting us to use root test, right? Because we see 3 raised by n, we see n plus 1 raised by n. But also we can use ratio test also. So some series we can prove by different kinds of tests. But this one, I'm guessing they use root test, right? Indeed. So they're saying, you know, try step 1, the series is not a familiar series. Step 2 is not an alternating series. 3, there's no upward series, which we want to compare to. Step 4, each term is power of n, so we can apply root test. So we take n's root. So we take a limit of 3 over n plus 1, right? That's just 1 over n. So the limit of this goes to 0. So by root test, the limit of this goes to 0 or less than 1, this series converges. It's not too difficult, right? It's doable, right? Okay, checkpoint. So let's all do this one. Okay, this one is a trouble one, right? If we don't have a 3 raised by n plus n, we think, okay, maybe we can use root test. But here we have 2 raised by n over 3 raised by n plus n. So try it. And then this one, the numerator 2 raised by n seems grows, well, it's an exponential function. The denominator is 3 raised by n plus n. The intuition is the denominator grows faster than the numerator. But try, so the intuition is this series should converge, right? Try to see which one, which test to use. Couldn't you use root with, can you do that? No, that wouldn't helpful, right? That wouldn't be helpful. Because this one, we cannot use a root test. Oh, okay, I understand what you mean. You mean we want to compare this one with 2 over 3 raised by n, right? Then this one is less than that. So you want to use comparison test, basically. And then you want to compare with 2 over 3 raised by n. Right, there are a couple ways of thinking this. You could compare with, because you could compare with a geometric series, right? 2 over 3 raised by n. Geometric series, 2 over 3 is less than 1, and which converges. And then what about this series? This series is less than that. It's a smaller one. It's smaller than the convergent series. So it must converge also, right? Maybe just try different ones, right, to see, because we still have time. We have a couple minutes. So try to do yourself. Think about, you know, try to follow those steps actually. Well, first remember this: the numerator is 2 raised by n. The denominator is 3 raised by n plus n, right? Maybe try to use this 5 steps. Okay, so anyone has any suggestions? I'll just leave this one for you, okay? So maybe we can talk about the next class. Think about, okay, so there's 2 raised by n over 3 raised by n plus n. Right, so my intuition is to compare with a geometric series, 2 over 3 raised by n. I only got the limit comparison test using geometric. Yeah, you could do that, yes. You could compare, you could use the limit comparison test with 2 over 3 raised by n. Yes. Yes, okay, great. And I will assign homework and the post, I'll remember the post on Blackboard also. Sometimes I forget. And thank you for someone reminded me. And I see you on Thursday, okay? And in between, if you have any questions, I'm happy to help. Just let me know, all right? Okay, have a good night. Thank you, have a good night.